welcome back for another Earth Science Lab video. This time we're going to introduce soils as well as weathering and erosion. So this is a multifaceted lab where we're going to identify the differences between physical and chemical weathering, as well as talking about the process of erosion. We'll also be introducing some of the physical and chemical properties that can be identified, both observed and interpreted in soils, which kind of then builds into within those physical properties, such as maybe grain size, or just even what it's made out of, or what layers are there, or what latitude they're at. We're able to accumulate that data and look specifically at the 12 soil orders that are found in the United States and across the world itself. We'll narrow it down to the 12, meaning that we've got these orders or taxonomies of what soil horizons and types are, and again it introduces and kind of includes all of those physical and chemical properties that we'll be discussing in this lab. So we've got a lot to cover in this lab, and I'm excited to share this with you. So that being said, let's get going. Alright, so let's start with part A, soil properties. Now, soils are composed of mineral matter from whether parent material, organic material, water, air. Before we begin, I think it's important to talk about, very quickly, the process of weathering and erosion. So weathering is the breaking down of that material, and erosion is a process of it being removed from that spot and then it's transported and deposited later down. So I'm going to use an example. This is a little small candy bar, and how this works really well as an example of what, in a sense, weathering is. So we have two types, really. We also have biological, but we're not going to talk about that one quite yet. We have physical and chemical weathering. Physical weathering, candy bar, teeth. Physical, if I were to spit this back out, you would know it was part of a candy bar, because I'm physically breaking it apart. But the moment that I swallow it and it goes into my stomach, the acids in my stomach will start to break it down. That's chemical weathering. So the difference between physical and chemical is just the action of perhaps a parent material, a large piece of granite or basalt, breaking down into smaller pieces. Chemical weathering is an actual reaction, that there's a chemical change. There's a formula change due to acids that can cause that. So there is like that weird area with like water. Water, when it freezes, turns into ice, that's physical weathering. But if the water contains a solution of acid, that acid therefore becomes chemical weathering. So they kind of work back and forth, but the main key here is that you have this process of weathering, both mechanical or physical as well as chemical, that break down bigger rocks into smaller rocks, and then can even dissolve and bring out certain minerals within that. So at the end of the day, these start to lay down flat. You start to deposit these things, as we've mentioned in other labs, looking at this form of a conformity, where everything's layered. Whatever's on the bottom is oldest, what's on top is the newest, which brings us into this first part of a soil property, which is considered the soil horizon. I did share another video on soil horizons as well that you can see. This is the same diagram that I used, and I explained it in the video. I shared it also below in the description of this video. But very briefly, the way that this works is that this is older in time, and as you move towards the right, it becomes younger. Now, the key with this that I want to point out is drawing a little box. This pink box here, which is enveloped around the R horizon. It does not get smaller. What ends up happening is it's actually moving down, and new stuff is moving up on top and moving up on top and up on top. So it's not actually getting smaller as we go down. It's that we're trying to get it out of the view because we know that now new layers are being stacked on top of one another. So I'm not going to go into too much detail because, again, I mentioned I have that other video that kind of goes into this. But again, refer to this figure. We know that we go from the far left to the right in time. And it works out to be about 1 centimeter to 1 inch, depending on the environment, for every 100 years of soil development. What you begin with at the bottom is your R horizon. As you can see, they're outlined down here. R is specifically known as, do a little line here, I'll use it's a grain. R is the parent material, or the solid bedrock. And then over time, because of that both physical and chemical weathering, some of the material will start to break down along that uppermost portion, which will then allow us to create a loose-fitting sea horizon, which is a layer of incomplete weathering. And then we often get this nice little O layer on top, which just stands for organics. The O horizon is fresh organic. So imagine you're mowing your yard, and instead of catching all the clippings, you just leave them on top of your yard. You're depositing a fresh O horizon that will slowly decompose, break down. When it decomposes and breaks down, it releases nutrients and acids, which can then further the weathering process. So you have this development that occurs over time. Beneath the O horizon, those nutrients are leached through. The material begins to break down, which then produces additional layers, such as your A horizon, which I like to call the topsoil. So A is the topsoil, so T-O-P, soil, which is that rich, dark, stinky, manure type soil you buy at Home Depot to put in your garden. It's decomposed organic material that is very rich in nutrients. Then beneath that is the B horizon. B stands for subsoil. It's underneath it. Great. Then sometimes you get an E horizon that's in between them. That E horizon stands for eluviated, or it's a transition zone. So I kind of compare it very poorly, but hear me out. It's like a sifter, and you put sand on the top and you're sifting, and some stuff goes through, but some stuff gets stuck along the grate, in that transition of what you're dumping there, what you're sifting through, and what's now done. That sifter that's like your E horizon. It's that transition zone in between there. So these are our soil horizons that develop. This is a perfect case scenario, this one on the far right hand side. Does every place have this? No, not every place will have all of these. Not all layers will have E horizons. Not all soil horizons will have even a profile. May even have an O. Think about places like, they're all covered in sand. There's very little vegetation out in these deserts, these big ergs of sand. So they're not going to have a rich O horizon. But then you go to places like the rainforest, or even to these like the Okefenokee swamp, where you've got these really thick layers of biodegrading organic material, where they have really thick O horizons. And so it does vary based on the climate, based on the latitude, based on the overall geology and stuff as well. Okay, so I'm going to keep moving forward. Again, if you need additional support, check out that video, which brings us to these attributes here. Oh, sorry. Number one, as I just jump through all that, says, refer to this figure, list some of the major changes you've noticed as you go from left to right. So itemize it. You have to write it all out and crazy, but itemize it. What do you notice? Like the main thing that you can say is that, I can see that as we move forward in time that there's more vegetation, that we have increased number of layers. And what other things do you notice that are different as you move from left to right? Perfect. Question number two brings back this image again. It says, have you ever wondered where aluminium or aluminum comes from, which we use in our cold beverage cans? So bauxite is an ore of aluminum commonly found in tropical and subtropical regions. The high level of rain helps to concentrate these aluminum oxides, usually found in both B and C horizons, after they have been leached from the upper horizon. So we take out this bauxite, which looks like a box of chicken pox. It looks like a mineral with a bunch of little dots in it, and we heat it with incredibly high heat, and we get two byproducts. We get the aluminum, we also get fluoride. That's another conversation for another day. So pretty cool. That's where we get aluminum from. So you don't actually just pull aluminum from the ground. There's a big process and only is found in certain areas. So it's a very important alloy that we use. So then it says, based on the description of 19.1, table below, label the soil horizons shown on each of the four soil profiles. Excellent. So I'm going to scroll down. So this is the activity here. Here are four random profiles. The key to success is to read through these. Read through them. So as an example, soil profile 1. Few horizons have formed because the parent material, or the R horizon, was recently exposed to weathering. There is some biological weathering activity initiated by moss growth. So your job is to go, okay, well, it's already said that biological weathering, we've got fresh moss growth, so that must be an O horizon. We've already acknowledged that this is your parent material, which is your R. And again, I'm getting these values from just 2 pages up, right? And then we have this other layer that's here. We have to decide, well, what should it be? And I'm going to go with the letter C, because I'm going to assume in this case that it's really that unconsolidated. It's just starting the breakup of the parent material. So I've now identified my layer. We're going to come back to these later in the lab, so I always just treat each one as its individual thing. I know that there's designs, colors, and patterns that kind of distinguish the horizons for us in these profiles, but just really treat each one on its own and be sure to read it. Like as an example, this one says caliche, which is a calcium carbonate deposit. It is found in the B horizon, so it already gives you some of the answers in the prompt. So go ahead and fill all of these out, and that will wrap up this table for this activity. Clear my screen and get back to my mouse, which then brings us to the next soil property, soil texture, which is really the grain size. All soil is made out of a mixture of sand, silt, and clay based on percentages. So we have, if you have a sample, that sample is 100% of my sample. There will be very distinguished percentages of that sample that will be sand, silt, or clay. Sand being the coarsest grain size, silt being the medium, and clay being the finest grain size. So what we can do in that sense is we acknowledge that we have these three horizons, three textures. I apologize. You've got sand, you have silt, and then you have clay, right? I have a video, I've shared this as well in the module and in the comment area below on how to do this, a nice long video, so I'm going to kind of jump through it so you can, but I'll show you how it's done, but if you need help, check that video out. So it's based on percentages, so perhaps we could say that we get the sample in our hand, add some water, rub it in our hand, and we'll say, ooh, this sample perhaps has, we'll say, 30% sand. So it's very coarse. I can feel that 30% of it is sandy. I could then say that, I don't know, we'll say that it's 50% clay. Clay is something that we're very familiar with when you get your soil wet, right? Because it can cake. You can roll it like a snake. It holds it together. And then silt would be the difference. We'll say it's about 20%, because the key is that all your percentages must equal 100% in total. So the way that this is done, and I'm going to show you just a little bit of it very quickly. I'll use a different color this time. I'll use, I don't know, I'll use blue. Perfect. As an example, let's do sand. Sand, as you can see, is found on the bottom. Sand by percentage, it goes from 0 to 100%. And the key with this is that the line is drawn the same orientation as the numbers. So what I'm able to do is go, well, the sand is 30%. So this is 0, this is 10, that's 20, this is the 30 percentile. So that means I move my line for sand following the orientation of the numbers, which means that my sample, the final name, will either be clay, clay loam, loam, or silt loam. So then I can draw another line. This time we'll make it a different color, I think. We'll go here, draw a line, do that. Maybe we'll make this one orange. We'll do clay. Clay, as you can see, is on the left-hand side, and we can see that it goes from 0 to 100%. And again, it goes, the line goes all the way across for this one, because it's oriented in the same direction in which the numbers are going. So this is 0, 10, 20, 30, 40, 50. Note that when I put it on 50%, the two lines are intersecting. Then you'll do your third line, which is silt. Silt's at 20%, and notice that all three lines will intersect on one of these colored boxes, which means instead of giving us all these percentages, you just give it the name clay. Simplified. Again, if you need additional support, watch this part again, or just check out the nice little lecture video that I shared, because I think it goes into more detail and kind of helps with that. So that's the process there. What you have here for question 3 is you have been given 3 sets of percentages. Find the final name. Easy peasy. Okay, and that being said, we wrap up on part A. Alright, so part B is soil orders. Now we're going to take into consideration the different horizons, some of the properties, the texture that we looked at, and some of those attributes, and now we're going to put them in some form of taxonomy. So it says in the United States, soils are classified into 12 categories called soil orders. This taxonomy is based on the dominant physical and chemical characteristics that make each soil order unique. Like many taxonomies or a classification system, within each category there are subdivisions that we can further narrow down the specifics and understand how that area looks and works. So we can see in this diagram, which is provided by the USDA, United States Department of Agriculture. This is looking at obviously a global spectrum. We can see that we have our 12 orders going from left to right, and then the last 3, which makes up 15, I know, but these are not necessarily ones that we're looking at. In most of the case, we have rocky land, shifting sand, and then ice or glaciers. So we're really going to be more focused on these 12 orders. And then within that, as we said, there will be, they all link together, and there's suborders and stuff like that. But nonetheless, a couple things that we want to look at. So before I come back to it, question number 4 asks us to evaluate this diagram. So I'm just going to evaluate it with you, and then you can hopefully fill in some of those answers. So a couple things that we like to look at as earth scientists are spatial distributions. What do we notice? Are there any patterns? So as an example, I can draw a line on this, and I'll pick a new color. Let's do green. This would obviously represent the equator. Do we see any spatial patterns? Anything that seems a correlation as to, along that line, do we see any certain color schemes that match? Like as an example, I can see there's a lot of this like salmon looking one, which is known as an oxysol. We can see also in areas where maybe you have found your world's deserts, right? We've got deserts across the landscape. We do know from previous knowledge that there is definitely a pattern with where they're located. We know there's a latitudinal pattern. So do we see common colors that are very common within those areas? Again, we don't really know what these mean yet, these soil orders, but we can at least look at the colors and go, okay, I can see that there is some correlation, some I see lots of this color here, this color there. Just think about as we get farther towards the North Pole or the South Pole, do we see new colors that have been introduced, or do we see a dominance or a prominence of a very particular or specific type of soil order? So those are things that you're going to kind of talk yourself through. And then once you've done that, we've then kind of completed question 4, which then allows us to go into more detail. So it says soil order descriptors. So it's very nice in a sense that it's broken it off into pairs. So we're going to, you'll see that a lot of these are very similar, but there's just a little bit of change within them. So as an example, we'll look at this first one together, entosols and inceptosols. So the 2 soil orders with the least soil weathering and development are called entosols and inceptosols. Entosols are soils that are recent, and they have the least number of horizons than any other soil order. For an example, they'll have a very thin O, maybe an A horizon will be in development. Otherwise, it's mostly that parent material. These are found in many different environments, places such as sand dunes, steep slopes, or just areas where the parent or the rock are horizon has been only recently exposed. Inceptosols are very similar, but what ends up happening is there's a little bit more. It's not just maybe 1 or 2 layers, maybe there's 3. So it's just a little bit more in that progression. So it does say that here. It says inceptosols are a little more developed than entosols. Inceptosols have a few more, perhaps a thicker O and A horizon compared to maybe a normal entosol. Perfect. So that being said, it says it is estimated that entosols cover about 18% of the world's ice-free land surfaces, while inceptosols make up an additional 15%. Additionally, these support the largest percentage of the world's population when compared to any other soil order. 20% of the world's population live in the inceptosol area alone. Perfect. So now it says return to question 2 at the beginning of the lab. So I took a screenshot of it to make our lives a little bit easier. And I'm sorry, I'm going to cover myself up a little bit for this. Oh, there we go. You can still see me. See? So here we have this image from earlier in the lab. So it says return to that table. Which one of the 4 soil profiles do you think best represents an inceptosol? So again, when you read through these, there's some very specific things. So again, I'm going to start over with number 1. It says very few soil horizons have formed. And you're probably thinking, okay, that sounds familiar. So I'm going to underline it. Plus, very few have oh, I don't know what that is. What to do? Oh, it won't let me do it. Anyway, it doesn't matter. Few horizons have been formed. Fine. Because the parent material was recently exposed to weathering. Go back here to entosols, and it says right here, let's see here, to soil orders with the least soil weathering. They are very recent, have the least number of horizons, more likely to be found in areas where the parent or R horizon material was only recently exposed. So this matches the best. You would say that sample, you go, okay, well in this case, soil profile number 1 best matches. Oops. Easy. Number 6, using your thinking cap, given that 1 in 5 people live in these areas, what impact do you think would have on the functionality of this soil? Explain your response based on agriculture, construction. Just kind of think about the big picture. So we've already established that this is mostly parent material. There's not a whole lot there, so it's not going to be really good for agriculture. But if the majority of the people live here, but there's not a lot of agriculture, that doesn't seem to make a lot of sense, right? So, I don't know, when you think about stuff like this, think about like the Mojave Desert. That's a great example. They may not be a quote-unquote entisol because there are, but anyway, just to put in perspective, I guess. Nothing really grows out there naturally. Can we force things to grow? Absolutely, you can force things to grow. You can go buy fertilizer and make your own thing happen, but most of these areas it's not natural. So why do we move to places like Palm Springs, Apple Valley, the Mojave, California City, Palmdale, Lancaster, right? That has this great population, but not a lot of those resources. So those are things that certainly can play into that role. So nonetheless, I'm going to clear my screen. You will do the same for oxysols and ultisols, so find which one best matches that. Then we broke it down in andisols, iridosols, and gelisols, and then we broke it down to finally these other groups. So it's going to ask you again to find out which soil order best matches each one of these. And then there's additional questions about that. And then that completes the lab. So I think the key to success, I'm going to scroll back to the top. The key to success for this lab is that if you need additional support, there are other videos. I've shared other videos that have, again, the soil texture triangle, soil horizons. Those are all shared here within your module and as well in this YouTube video. I know this is a crash course real quick into weathering and erosion and dealing specifically with soils. The lecture material partners quite well with this, and I hope that this was helpful. Be sure to like this video down below. If you've not subscribed yet, please do so. Otherwise, leave comments below if you have additional questions, support, whatever comments, whatever you'd like to do. And thank you again for your time, and we'll talk soon.